Okay. I'm going to talk about some basic results in this lecture. These are things that, just bread and butter that are used when you actually use this as math. Okay. So start off, let alpha be a real number and let f and g be bounded functions on the closed interval AB. Suppose they're Riemann integrable. Then alpha times f is Riemann integrable, and the integral from a to b of alpha times f is alpha times the integral from a to b of f. F plus g is Riemann integrable, and the integral of f plus g is the sum of the integral of f plus the integral of g. And the absolute value of f is Riemann integrable, and the absolute value of the integral of f is less than or equal to the integral of the absolute value of f. Okay, let's prove some of this stuff. Note that if f is continuous at t in the closed interval AB, then so is alpha times f. It follows that the set of discontinuities of alpha times f is contained in the set of discontinuities of f. By the Riemann-Lebesgue theorem, the set of discontinuities of f is equal to 0, so the set of discontinuities of alpha times f must also be of measure 0. Therefore, alpha times f is Riemann integrable. From this, it follows that the limit on p of Rp alpha t exists for every choice of t and is equal to the integral from a to b of alpha t. Okay. Now, we can take that Rp alpha f of t and by very simple rewriting find it is equal to alpha times Rp of ft. Since the limit of Rp-ft is equal to the integral from a to b of f, it follows that the limit Rp alpha t is equal to alpha times the integral of a to b of f. Therefore, our result on this follows that we can factor out the constant from the integral sign. All right, so now if f and g are both continuous at t, then f plus g is continuous at t. Consequently, the set of discontinuities of f plus g is contained in the union of the set of discontinuities of f with those of g. Since both sets of discontinuities of f and g are of measure 0, the set of discontinuities of f plus g is of measure 0. Therefore, f plus g is Riemann integrable. Since f plus g is Riemann integrable, the limit of Rp f plus g of t exists and is equal to the integral from a to b of f plus g for any selection of t. However, okay, Rp f plus g of t is equal to the sum of I equal 1 to n of f plus g of t, which we can then, rewrite as the sum of these two Riemann sums. Okay. And therefore, by taking the limit on both sides, we get the result that we desire. Okay. As in the previous two cases, the set of discontinuities of the absolute value of f is contained in the set of discontinuities of f. This is because the absolute value function is continuous. Since the set of discontinuities of f is of measure 0, therefore the set of discontinuities of absolute value of f is of measure 0. As a consequence, the absolute value of f is Riemann integrable. Since for any x in the closed interval a, b, f of x is between negative absolute value f of x and positive absolute value of f of x, it follows that the Riemann sums fall in this way as well, this order as well. Since all these functions are Riemann integrable, the limits on P exist. The limits will preserve the order. Therefore, we get that these integrals fall in this order. And I can then factor out the -1 here. And so we have a number that is trapped between another number and it's negative. Therefore, its absolute value is trapped less than that number. And we are done.